Sulfonamides.
Overview of sulfonamide. Sulfonamides were the first effective antimicrobial drug. It was structurally similar to para-aminobenzoic acid, its compound that necessary for bacterial growth. The sulfonamide antimicrobial, it's able to block the normal utilization of para-benzoic acid into folic acid. First, we identify the functional group since the sulfonamides have two functional groups, the Sulfonamaide Group and the Amino Group. According to the priority, naming starts from the sulfonamide. Then we identify the parent longest chain. Here in this example we have a benzene ring since its name called benzyl sulfonamide, and the numbering starts from the sulfonamide that give the longest chain. Then, since we have amine group on number 4, the general name of this structure is called 4-amino-benzyl sulfonamide.
Looking at the structure of the sulfonamide. Sulfonamide are a composite of the silver atom that has two sets of the double bond to the oxygen atom and a carbon-based side group and a nitrogen atom bound to the silver itself. In organic chemistry, in more precise sense, the sulfonyl group considered to an amino group. Relatively speaking, this group is unreactive. The amine center is no longer basic. The SN bond is cleaved with the difficulty because the rigidity of the function. And when we change the carbon group, the drug product is changed.
Chemical properties of sulfonamides. It is often assumed that sulfonamide compound behaves in a similar manner to carbonyl compounds, such as esters and amides, and related sulfur compounds, such as sulfone, sulfoxide, and sulfonate esters. While there are many more interesting differences in their reactivity, which are highlighted below, and from the basis for much of the synthetic utility of this group. At the beginning, I will talk about electron withdrawing capacity. Sulfonamides as well as carbonyl compounds, sulfones and sulfonate esters all exert an electron withdrawing effect on surrounding atoms, both mesomorphically and inductively. However, the effect of sulfonamide is the least electron withdrawing compound. Scheme number 1 explains the electron withdrawing effect of the carbonyl group. Second, as a leaving group. Sulfonamides can also act as a leaving group under certain conditions, often with the elimination of sulfur dioxide. Scheme number 2 also tries the sulfonamides group, which are a good leaving group, same as carbonyl group. Third, resistance to nucleophilic alpha-substitution. One of the most striking differences between carbonyl compounds and sulfonyl compounds is the resistance of the latter to nucleophilic displacement of leaving groups at the site alpha to the sulfonyl unit. The sulfonyl groups deactivate this site, whereas the carbonyl groups and other electron withdrawing groups such as nitrile activate it. The effect is easily demonstrated by comparing the reaction of alpha-chlorosulfonyl compounds and alpha-chlorocarbonyl compounds with potassium iodide in acetone. Scheme number 3 explains the sulfonyl compounds are essentially unreactive, whereas the carbonyl compounds are readily substituted. At the scheme number 4, we can see the reaction of alpha-chloromethane sulfonamide with amines and phenoxide react similarly to other sulfonyl compounds. Indeed, it was noted that reaction number 3 of phenoxide with the chloromethane sulfone anidine failed to yield any displacement product, and the reaction number 4 of phenoxide with the chloromethane sulfonamide after treatment with aniline for 14 days had released only 23% of its halogen. Figure number 4 shows difference between alpha-halosulfonamide and alpha-carbonyl compound. The origin of this deactivating effect has been attributed to the steric and polar effect as described by Ingold. The approach of nucleophile to the alpha-halosulfonamide is hindered by atom of high electron density. This is in sharp contrast to the comparable approach to an alpha-halocarbonyl compound, where the approach is essentially unhindered and quite possibly actively assisted by interaction with the vacant pi orbital located on the carbonyl-carbon atom, which lowers the energy of the vacant sigma orbital of the carbon-hydrogen bond and facilitates nucleophilic attack. Fourth, carbonyl and amide acidity. There is unusual dichotomy in which the sulfonamide group stabilizes the alpha-carbonyl less than corresponding amide, pKa 13 for a sulfonamide alpha-carbon hydrogen group, and 25 for amide CH group, whereas the nitrogen-centered anion is stabilized more by the sulfonamide than the comparable amide, pKa 25 for an amide NH compared to the pKa 8 for a sulfonamide NH.
Alkylation of other gamma and delta sultones with iodotrimethyl followed by treatment with fluoride led to the desulfurized products with simultaneous methylation in a reaction sequence that once again showcases the anion stabilizing capabilities of the sulfonamide and its ability to act as a leaving group under specific reaction conditions. Seed deprotonation of the sulfonamide could be facilitated by the attachment of tetrahydropyranyl moiety to the sulfonamide nitrogen atom, which stabilizes the alpha anion via acylation effect and highlights the propensity of alkyl sulfonamide in their methylated form to pair the metal and electron density on the carbon atom, rather than the sulfonamide oxygen atom, demonstrating their different reactivity compared to carbonyl compounds. The major product arises from the non-equilibrium between methylated sulfonyl compounds, which leads to the indomethylene. Exposure of this compound to tetra N-butylammonium fluoride in tetrahydrofuran then leads to the desulfonylated product in good yield. Compound 11 could undergo the unusual displacement process at the alpha position of a sulfonamide by virtue of the process being intramolecular. The mild electron withdrawing capacity of the vinyl sulfonamide and the resistance to undergo competing intermolecular addition and the allowed intramolecular displacement reaction of these compounds and the leaving group propensity of the sulfonene unit to develop a mild reduced-selective synthesis of oxazoles.
The synthesis of pyrroles, stilbenes, benzo-C-sinolines, and dibenes C-amine acridines from sulfonamides. Rearrangement of an electron-rich aryl ring linked to an electron-deficient aryl group by a sulfonamide. Heating these compounds with base and dimethyl sulfoxide lead to the pyrrole products in moderate to good yields. The general scheme and mechanism are given in this synthesis 7. The reaction is successful for a variety of aromatic systems, providing that, number 1, at least one site ortho to the nitrogen atom is unsubstituted. Number 2, the hydroxy group in the same ring AR1 is appropriately positioned to direct nucleophilic attack on the second AR2 electron-deficient ring. Number 3, there is an electron withdrawing group suitably positioned in AR2.
The ability of the sulfonyl unit to behave as a radical leaving group while pursuing a synthesis of functionalized heterocycles discovered that the aryl group from the sulfonamide under free radical conditions could migrate to a pendant alkyl group with a loss of sulfur dioxide.
The mechanism was shown to be an ipso attack of the primary radical onto the aromatic ring bearing the sulfonamide followed by elimination of SO2. Much work flowed from the group of SPICAM in exploring the application and scope of these reactions. The same strategy was later exploited in the preparation of pyrrole systems such as 5 and in the synthesis of tricyclic systems such as 6. As was observed, the competing reaction of direct addition of the radical to the aryl group was also obtained in varying amounts.
Treatment of nitrogen aryl aromatic sulfonamides with alkyl lithium reagents led to ortholithiation, followed by an unusual rearrangement in which the diaryl sulfone was formed.
As for the physicochemical properties of sulfonamides, we see that all sulfonamides share the same core structure, but differ in the side moiety. The differences in the side moieties gives rise to a large number of compounds, which may exhibit the same properties, but at different levels. As for example, we see that sulfonilamide has a water solubility of 750 mg per liter, which means that this compound is fairly water soluble. Also, it has a melting point of 165 Celsius and a boiling point of 400 Celsius. However, it may be degenerated before it's reached its boiling point. Also, due to the protonated amino group, this compound has a pKa of 10. As for our next example, we see that sulfadimidine has the pyrimidine as a side moiety, which is a very miscible in water. As we can see that the water solubility for sulfadimidine is double the water solubility for sulfonilamide. Also, the melting point here is more than the melting point for the sulfonilamide, which is here is 178 Celsius. And you can see that the pKa is lower, as we have here a pKa of 7.45. That means that this structure or this sulfonamide is more to be an acid than to be a base. And for our last example, we have the sulfapyridine. As we can see, the side moiety in this sulfonamide is the pyridine. This side moiety lowers the water solubility for sulfapyridine to 270 mg per liter. But we can see that the melting point is higher than the other two sulfonamides that we mentioned, as the melting point for sulfapyridine ranged from 188 to 191 Celsius. Also, the pKa for sulfapyridine is 8.54. That is a value in between the sulfonilamide and the sulfadimidine.
This is the general structure of simple sulfonamides. In order to discuss the SAR of sulfonamides, we divide the structure into 4 parts: N4 amino group, aromatic ring, sulfonamide group, and 1 amino group. This is the amino nitrogen and it's attached to 4 position, so it's called N4 amino group. This group is essential for activity, so if we replace this group with any other groups, this results in loss of activity. Substitution on N4 nitrogen results in 2 types of activity. Either it can result in prodrug or inactive sulfonamides. This sulfonamide undergo metabolism by an acetylation reaction to produce N-acetyl Sulfonamide. We can observe on nitrogen atom the acetyl group. This substitution makes the compound inactive metabolite. In the structure of the drug sulfasalazine, we can observe this group, which is attached on N4 amino nitrogen. This substitution makes the compound prodrug. It can be metabolized to produce 2 active metabolites. We can observe the azo linkage here between the 2 nitrogens. This linkage can be cleaved by the enzymes azoreductases within gut wall to produce 2 active metabolites. Succinylsulfathiazole is another example on substitution on N4 amino group that makes the compound a prodrug. The succinyl group is attached to form a prodrug for controlled release of the drug sulfathiazole. This is the aromatic ring. We can observe it is a phenyl ring. This aromatic ring is essential for activity. Replacement of this phenyl ring with other groups or ring systems results in the loss of activity. This aromatic ring is substituted with para-amino group, which is important for activity. If the phenyl ring is ortho or meta-substituted, this will result in loss of activity. Sulfonamide group is essential for activity and shouldn't be replaced with other groups like carboxylic acid and amide groups. This sulfonamide group should be directly attached to the aromatic ring without any carbon between them. This is one of the very important groups, which can be modified to produce a different types of sulfonamides. This nitrogen should be primary or secondary. When N1 amino group is monosubstituted, this can increase its activity when the substituent is heterocyclic ring, which result in highly potent drugs. Sulfonamides that contain a single benzene ring at N1 position are toxic. When N1 amino group is di-substituted, this results in loss of activity. In these examples, sulfasalazine and sulfamethoxazole, we notice heterocyclic rings on nitrogen, which increases their potency, and this will bring the pKa value nearer to the optimum pKa value, resulting in more antibacterial activity and less risk of crystalluria. So, introducing of heterocyclic rings increases the potency of the drug. That's why we can observe most of the sulfonamides are substituted with heterocyclic rings on N1 nitrogen.
The synthesis of a new sulfonamide from sulfon to sulf9 was performed in two steps. Firstly, the synthesis of 4-hydroxy-2-isopropyl 5-methylbenzene-1-sulfonyl chloride, which abbreviated as CHS. CHS was obtained from the reaction of carvacrol to 6 equivalents of chlorosulfonic acid. This reaction occurs instantaneously at 0 Celsius to give CHS a plus amino group which combined with R group. This reaction to complete will consume 3 to 6 hours with the presence of dichloromethane to give sulfon to 9 products. Actually, this R group will determine which sulfur product that we will gain. If the R group is methylbenzene, the product is sulfon. If the R group is nitrobenzene, the product is sulf2. If the R group is fluorobenzene, the product is sulf3. If the R group is orthohydroxybenzene, the product is sulf4. If the R group is methoxybenzene, the product is sulf5. If the R group is naphthalene, the product is sulf6. If the R group is pyrazine, the product is sulf7. If the R group is phenylsulfonyl that conjugated with thiazole ring by amino group, the product is sulf8. And the last one, if the R group is metadinitrophenylamine, the product is sulf9. The reaction of 4-acetylaminobenzene sulfonyl chloride with 2-aminopyrimidine will give an acetanilide derivative, which is N,1,2-pyrimidinyl sulfanilamide. The subsequent hydrolysis of this product with a base leads to formation of the desired sulfadiazine. A chlorosulfonation of acetanilide with excess of chlorosulfonic acid affords para-acetamidobenzene sulfonyl chloride, which is an essential intermediate for the synthesis of sulfonamide drugs. Aryl sulfonyl chlorides are converted into corresponding aryl sulfonamides by treatment with concentrated ammonia solution. Para-aminobenzene sulfonamide is obtained by converting para-acetamidobenzene sulfonyl chloride into the amide, with aqueous ammonia and then selectively removing the protecting acetyl group by boiling with aqueous hydrochloric acid.
Microwave synthesis of sulfonamides directly from sulfonic acid. The generation of sulfonamides directly from the sulfonic acid or its sodium salt under microwave conditions using the mild chlorinating agent 2,4,6-trichloro-135-triazine in acetone with triethylamine that will form an acid chloride. After filtration, sodium hydroxide and the amine were added and the reaction mixture was exposed to further microwave irradiation. This methodology worked well and giving the sulfonamides in a good yield. Microwave-assisted synthesis of sulfonamides from pentafluorophenylsulfonate esters. A convenient preparation of sulfonamide, the microwave-assisted displacement of pentafluorophenylsulfonate esters 3 with amines. The pentafluorophenylsulfonate esters were easily prepared from the parent sulfonic acids. It was shown that the employment of microwave irradiation allowed the preparation of sulfonamide libraries rapidly and without chromatographic purification being required.